Good morning, good afternoon, or good evening, wherever you are. My name is Jan de Geer. I'm the director of Research Institute Matrix. Today we'll have Javier Tordable as a speaker. Javier works and lives in Seattle and at the office of the CTO, Google Cloud. And I'll keep this introduction short because Javier will talk a little bit about himself later during his presentation. Suffice to know that Javier studied mathematics back in Spain, even started a PhD, but then was quickly seduced by the Microsoft and work over there. Very much looking forward to this talk. If you have any questions, please put them in the Q&A. At the bottom of your screen, you should see a Q&A function. We'll address all questions at the end of the presentation. All right, over to you, Javier.
Thank you very much, Jan. I will present. Okay, I hope you can all see my slides.
Yes, we can.
Perfect. First of all, thank you for inviting me, Jan. I'm very humbled. I've prepared a presentation for you with a series of interesting questions that have come up in conversations that I've had over the past few years, and I hope you will find it interesting. In this slide, you can see my Twitter handle, my name, and LinkedIn. I'd be happy to chat offline on anything that we may not have time to cover today. These are the things that I wanted to talk about today. I'll make a brief introduction to myself and especially what I do. Then I will talk briefly about where mathematical problems come from, which I think is relevant because I will suggest a few areas where we can find interesting problems where you may not have looked before. And then I'll cover a variety of questions, which I try to structure within these three groups. Why the three groups? Well, I imagine they would look familiar to all of you. Don't worry if you can't read the left side of this slide. It's not meant for you to read. It's just a screenshot of my LinkedIn profile. But let me give you a few highlights. As Jan was saying, I studied computer science and mathematics at the University of Valladolid in Spain. These are two separate degrees rather than a dual major. So I basically went through the full curriculum for both of them. Then I joined the PhD program in mathematics, but I was seduced by Microsoft, so I left soon after. Imagine some of you are graduate students or PhD students, so I won't talk about the reasons why I decided to drop out, so I won't make you miserable. But one important point that I want to make is that I'm not a professional mathematician. I've never been a researcher, and all my experience has been in a professional setting as an engineer and now as an executive. I imagine also executive is not a polite word in some academic circles. It's what you would call somebody who can't do technically complex work anymore. So let's just stick with engineer. Also, I'm not an expert in a lot of the areas that I'm going to talk about today. My experience has been building software, which is something that I've been doing fairly successfully over the past almost 15 years. The majority of that time has been at Google. In spite of the fact that I'm not a mathematician, I think I still have a bit of an intuition about what problems may be interesting for mathematicians. So let me tell you a little bit about what I find this type of problems. I work in Google Cloud. Cloud is a team where we sell compute infrastructure. 5 or 6 years ago, when cloud was getting started, it was all about saving money. Instead of spending hundreds of millions of dollars building data centers, someone would pay a cloud service provider only for what they use, and they would move their IT and their research and other computer applications to this new infrastructure. Now, the cloud today is mostly about bringing new capabilities, about doing things that most companies just can't do by themselves. For example, leveraging big data or using AI to do things that couldn't be done before. In some ways, cloud is where companies do their artificial intelligence or research or their most innovative projects. So in my role as a technical director in Google Cloud, I regularly talk with executives, CTOs, engineers across a variety of industries and the problems they face. So for example, when a CEO or a CTO of a large company has a bright idea and thinks, well, I want to use the cloud and AI and do something amazing that raises my stock value and gets me in the news and maybe start a new billion-dollar line of business. They come to us and ask, well, what should we do? And we go, well, what do you make? and they may say, we build cars, and we talk about digital in-car experiences from maps to entertainment systems, to live streaming games to the car, or we can discuss programming robots in the assembly line to make sure to make manufacturing more efficient, to adapt to customer demand faster, and so on. Or they may come and say, we deliver packages, and then we can discuss fast optimizations to their logistics network or autonomous delivery drones. I've personally spent a couple of years working with some of the largest video game companies in the world, and others in media and entertainment. So a lot of my conversations have been about how to make video games better, how to use video game technology for other purposes outside of games, such as visualizations in engineering or architecture, or using video game worlds for simulated training data for AI systems, which is something that's very much in vogue right now. And at the moment, I'm working in the healthcare space. So some of the conversations I've been having lately are about how to use AI to optimize drug discovery or to improve management of chronic conditions such as diabetes. So all these conversations that I regularly have led me to think that I can maybe provide you with a perspective about what types of problems may be interesting to work on coming from the industry. And just as a quick aside note, a few years ago, I did a presentation about examples of interesting mathematics that are used across a variety of products at Google, which a few people found interesting. So when Jan reached out a few months ago and asked if I was willing to do a presentation for you along the same lines, well, my first reaction, looking at the previous list of speakers, is that I can't really tell you anything that would be the same level, so I'm just not going to try. And that's why this presentation is a little bit different. My second reaction is that the presentation I did almost a decade ago is already incredibly out of date. When I was going through the examples, most of them have been replaced one way or another with machine learning systems. AI, machine learning in particular, has had a truly transformational effect in the way that Google operates, and I believe it's in many ways similar at other top technology companies. This transformation has not been restricted to Google, but it's broad across the technology space. So all the material that I'm going to talk about today is original, in the sense that it's not in that presentation. It's based on some of the conversations that I've had over the past couple of years in my day-to-day job. These are very open-ended questions, but I hope you will find them interesting. And also, one point that I wanted to make is that I think it's worth pondering about where mathematical problems come from. So from what I understand, the majority of problems that mathematicians work on come from either mathematics itself in its most pure abstract form, or from closely related disciplines, especially physics and a few select fields in engineering. In my view, mathematics is a very inwards-looking discipline. And many of you probably wouldn't have thought about looking at areas such as computer science, the health or social sciences, or manufacturing or logistics, as a source for inspiration for problems to work on. So when I look back at the time when I was a student, I think I was very attracted to mathematics in part because of the pure intellectual exercise. And in this context, sometimes thinking about money or the economic impact of a problem feels a little bit dirty in a way. But we can also think about money as a measure of how much value society puts in a specific problem. So whereas a lot of the classical problems in mathematics don't really have a high monetary value, most of the problems that I'm going to talk about today are worth real money. So this image that I included here, as you would have imagined, is from Euclid's Elements. So as you probably know, the very name geometry comes from the Greek words for geo, or earth, and metros, or measure, right? Back then it was important to measure distances on Earth because in the Greek civilization, trade and moving merchandise by sea was critical for progress and for the economy. So I guess in some ways you could have considered this as applied mathematics. And finally, before I delve a little bit deeper, let me confirm that there's not a single equation in this presentation except anything that I may have inadvertently missed in some of these images. So let me begin with algebra-like problems. And I'll start with a brief introduction. What is AI, artificial intelligence? I think the definition is changing. Initially, it was a discipline of relatively simpler algorithms by today's standards. So it mimics actions that when taken by humans represent intelligent behavior. And the image here represents one of the most commonly used algorithms, which is graph search. When we have a game like tic-tac-toe here, but it will be the same in chess or other games, we can map the current state of the board as a node in a graph, and each possible legal move as an edge that takes to another node. Then one way to win the game is to build a full graph and figure out which potential move is more likely to lead to a win. So given the constraint that we don't know what move an opponent may make, we have to consider probabilities across these potential paths. So I want to make two observations about this. The first one is that this example is purely discrete. Each state, each edge represents a discrete entity. There's no such thing as making half a move. The second one is that the spaces in which these algorithms try to find a solution can be very big. There's a combinatorial explosion in a way. So we start from a board in chess, for example, and there are dozens of moves. After a few turns, we end up with many millions of potential options. There are smart ways to restrict how deep and wide we search, but eventually we find that the search space is just too big. So in the game of Go, for example, one of the reasons most researchers thought it was impossible at the moment, back then, a few years ago, was because this search space is massive. There are more potential games of Go than there are atoms in the universe. Of course, as you know, or as you may know, machines are now better than humans at Go after a very successful project by Google's DeepMind, which is called AlphaGo. But it works in a slightly different way, and beating humans is certainly not the same thing as solving the game. On a different game, game in quotes, right? We can look at theorem proving, for example, in particular, manipulating expressions, symbolic expressions, in order to obtain other expressions, in a way that if we start from a set of established actions and all our moves in this game correspond to correct symbolic manipulations, then we come up with theorems. This is also a problem that was studied for a long time and share those same two characteristics. It is discrete, and the combinatorial explosion makes it intractable, except for some relatively simpler cases. So the end result is that we know this approach was just not good enough to do interesting mathematics. And I'm sure some researchers in the area would argue with me on this, but I think we would agree that we're very far from having AI doing real research in mathematics. So in contrast with this, there's an entire different category of AI algorithms, which are machine learning algorithms, and in particular, deep learning. So these algorithms rely on statistical properties of the data and are based on learning these statistical properties in order to do smart things. So one typical problem that you have in AI is to identify objects in an image. If you try to do search in the pixel space, you'll find it really hard. An image from a phone camera, for example, could have 8 million pixels, each one with 16 million colors. There will be many trillions of potential images. There's a lot of possibilities to build a search tree. Instead, what we do is we rely on certain structural elements in the image, as well as statistical regularities. And the beauty of this is that the algorithm finds both in the course of its training. So when we're training, we take a lot of data that we know to be correct, like the bounding boxes that you see in these images or labels, and we use that to build the algorithm. So one issue with this method, of course, is that we need data, right? And the more complex the problem in general, the more data we need. But keep in mind that a couple of interesting differences with the previous approach. This set of methods are inherently continuous in a way. I hope you can see my air quotes. Obviously, everything in the computer is zeros and ones, right? But we can think of the positions of the objects or the probabilities of recognizing these objects as continuous. The second one is that these methods are never 100% precise. Sometimes a small difference in the data results in a big difference in the result. A small dog may look at a cat, right? Or the algorithm cannot tell the difference. So whereas with symbolic methods, we're typically precise, deep learning methods are not. So for curiosity, you can see in the right side an example algorithm for image processing. It's a neural net called Inception. Deep learning is called that way because these algorithms or ML models, can be many, many layers deep. But one interesting benefit of this type of methods is that they work well when we have very complex, abstract spaces, like, for example, language. So one common task is to build an encoding of words into binary vectors. And we can do this for millions of words. But continuous methods are not good at manipulating millions of independent features. So we can transform this into a smaller space. For example, 2 or 100 or 1,000 dimensions. So this is typically called the language embedding. I'm not sure if it's a misnomer or not, because the vectors in the first space are not in the second space. It tends to be a much smaller dimension, but this is a terminology that is used in machine learning. So you can think of a language embedding as a function from words onto vectors in a space of relatively small dimension, a few hundred maybe. But with this, with the characteristic that we can do smart things with these vectors. The most famous one that you can see here is that we can add and subtract words. And this leads to interesting approximations like what I show here. So the details of how this is done, autoencoders and how it's used within information retrieval and so on is not important, but I want to make 2 points. These methods have been incredibly successful for some tasks, like language translation, but they are imprecise by their very nature. So we know for certain that this approach is not good enough for precise reasoning. We can't use this to prove theorems, not just in mathematics, but pretty much in any science. We know how to build systems that are good enough to write news, for example, especially sports, financial learning reports, and so on, where there's a little signal to noise ratio. And we can even write fake news in the political arena in a fully automated way, which obviously has repercussions in society. But we can't write a scientific paper with this. My personal opinion is that we probably will never be able to do that just with deep learning methods. So here is the first problem that I think it's worth looking at. We have been building incredibly large models. GPT-3, for example, which is a language model created by OpenAI, has almost 200 billion parameters with a B. So you think that normally just a few thousand words are enough to speak a language, then this model has millions of parameters for every single word. They're very, very complex objects. But in spite of that, we have very little understanding of how embedding spaces work. For example, how close are the, this type of language embedding spaces, like how close are they to vector spaces? Are Euclidean spaces even the right structure for this type of embeddings? Is there any way that we can build embeddings where we can do interesting calculations with words, maybe even do something similar to symbolic reasoning? One interesting success, which is fairly recent, is the ability to translate across many languages without having to go through English, which is translation across many different pairs of languages independently, but with the same large-scale model, which is a result that a Facebook research team accomplished recently. So this raises the question of whether there's a deeper structure of concepts, of ideas, and whether these ideas can then be projected in a way into words in different languages. Like, is there a way that we can think of concepts or ideas, some kind of space or graph, and the words as projections within a specific language plane? Can something like this, be properly defined? I don't know, but I don't think anybody has studied, this systematically. In some ways, the relation between these two schools of AI goes back a long time. In the 80s, for example, the first AI winter, machine learning proved unsuccessful solving even simpler problems, which leads to, the symbolic camp declaring victory. But for the last decade, we have seen tremendous success by machine learning. So maybe a key moment was Hinton, Bengio, and LeCun winning the 2018 Turing Award. But now people are starting to be very aware of the limitations of deep learning. For example, the ability to learn when there is little data. It's called one-shot or a few-shot learning. On the left side in this image, you have Gary Marcus, which is a well-known researcher who has been leading this trend towards more symbolic or hybrid systems, which try to leverage the benefits of traditional AI. On the right side is Danny Lang, currently at Unity, who's in the camp of bigger and better systems. In particular, Danny has been doing a lot of work on simulation, which is essential for systems that require more data that we can even produce in the real world. recently had a chance to record a session with him for the Unity AI Summit, where we talk about simulation for industrial use cases, which I think may be interesting for some of you. So from all this, I think the second problem that we can think about is whether these discrete and continuous methods of symbolic AI and machine learning can be combined in a smart way. For example, something that uses deep learning to come up with a schema of a proof and symbolic AI to properly fine-tune the details. So as far as I know, there hasn't been a lot of research here. More generally, where you know, a lot of research and money has been spent in creating complex AI models to solve tasks like detecting objects and images or training robots to solve the Rubik's Cube, but not enough research have been spent trying to understand if the state-of-the-art models that we have now, like GPT-3, could be used for symbolic or mathematical reasoning, the kind of, you know, hybrid approach. Okay. Now, going in a slightly different direction. A big reason deep learning won over other AI methods is because it's fast. This is something that computer scientists understand at a cultural level, even though it's a bit harder to notice for folks in the pure sciences. When you have something that is twice or 3 times faster, that may not necessarily be transformational. When it's something that's 100 or 1,000 times faster, it will change the way that things are done. So even with the need to process a lot of data, it's much faster to feed that to the machines and a deep learning model than it is to have humans try to devise clever tricks for programs to behave intelligently. So this idea of deep learning being fast and using many machine learning algorithms is so important that many companies have spent millions and billions of dollars creating hardware that basically just runs machine learning algorithms. So what you see here is a chip. It's called a Google TPU. This is part of the reason why you have speech to text in your phone, for example. If you tried to do that 10 years ago, you would have needed a supercomputer, and it would not have been a free product that anyone can use all the time. So part of the reason we enjoy these kinds of things for free is that computer scientists have been able to make these calculations incredibly fast and cheap. So one key observation is that the reason Google had to do this is that normal chips were just not fast enough. And the advances that were coming up from the regular manufacturers were just, you know, too slow. This is another example of a company building their own hardware. You may have heard of the new M1 chip that Apple designed, and it's included in their new Mac line. Certainly, they do a lot of smart things in this chip, but the point that I want to make is that the reason they had to do this is because they were not getting fast enough development from the regular chip manufacturers. So as a matter of fact, this is typically discussed in the industry as the end of Moore's Law. For those of you that may not have heard about this, Moore's Law was a principle established by one of the founders of Intel that talked about the rate of development for microprocessors. So this principle held for decades, and it's hard to overstate how important it was for our society. But the computer that you carry in your pocket is orders of magnitude more powerful than the computer that helped put humans on the moon, right? You know, it's in a tremendous rate of progress. So the fact that this trend has ended, I think is quite a big idea. It's actually been over for a few years. This is part of what led these companies to build processors that are tailored for their own purpose. And I think it's a big idea, so let me repeat it. One of the major trends that has shaped human society over the last few decades, you know, together with the internet and globalization, is over. So all the hopes that computers will just continue getting faster and faster until we reach the singularity will not happen. It's not going to be that easy. So this opens up the door to think about things like, can we make chips faster? Or can we make software more efficient? Or maybe more interesting for you, can we make algorithms faster? For example, we can think about how to make optimal algorithms. We certainly don't know optimal algorithms for all the commonly used tasks that we do with computers. So you may be thinking, well, isn't this a computer science program? Let me give you an example. A very common algorithm is sorting. Think of it as taking a list of natural numbers and leaving it in order. So this is the sorting problem. We know that we use, we use algorithms based on comparing elements, so that there's an optimal solution. We can prove that. It's in the order of n log n. Well, in general, it takes n log n comparisons to sort these numbers. But there are other algorithms that don't rely on comparing elements one by one. So for example, in the left side here, there's a sorting network for 4 numbers. sorting networks are inherently parallel, so they can sort numbers in the order of, log n in an optimal case. So you can think of it as numbers moving from left to right, all in unison and being put in place as they move through each node. Well, it's possible to prove that there indeed exist optimal sorting networks that achieve that order of, log n. This requires understanding the concept of expander graphs, and the existence of these expander graphs for a given graph size, for example, can be proven by the fact that we know how to build Ramanujan graphs, and these Ramanujan graphs happen to have very interesting properties. For example, we can define a theta function of a graph based on certain paths within the graph, and we can define equivalent first on those paths, and we can call them primes. And this zeta function is defined as a product that occurs those primes in the graph, this is the hierarchy function of the graph. There's the analog of the Riemann hypothesis for the zeta function of the graph, and it just happens that the Ramanujan graphs are precisely the ones that satisfy this Riemann hypothesis for the Ihara zeta. There's not nearly enough time to explain this in detail, but the key idea that I'd like to share is that we started from a well-studied problem, which is sorting numbers. And we ask a question, which is, what is the optimal algorithm? And this leads us to interesting mathematical concepts and problems. So as we face harder and harder constraints for chip design and, all those pesky limits like the speed of light, I think it's going to become increasingly important to think about what else we can make optimizations, right? And I think one idea that is very interesting is to look at the algorithms that we most commonly use and think about the theoretical optimal efficiency. Let's move on. This is actually the next one is my favorite set of problems that I'm going to talk about today in geometry. Within computer science, we sometimes think of different representations of graphs, which are useful for different things. So if we have a really large graph, like a social network, we can use an adjacency list to get the list of friends of a person, for example, which is much faster than doing a scan in a large matrix of data. But if we're trying to calculate, say, the number of walks from one edge to another, then the adjacency matrix representation gives us in a more direct way. And maybe representation is not the best mathematical term here, but you can think of it as the structure that we use to model a particular object. So do we think of it as a set of numbers or a matrix over a ring or field or an element in a particular geometric structure and so on? So again, within computer science, we have 3D geometry, and we also have multiple representations. So on the left side, you see a mesh. Typically, these are triangles, and this is by far the most common representation. In the middle, you see voxels. These are essentially little cubes. They're sometimes used, for example, in procedural generation, but you can think of them as a way to discretize the space. And in the right side, you have NURBS, which are essentially objects defined by equations, which are used, for example, in ray tracing. These will be most familiar to a mathematician, but they're used fairly infrequently in industry because they're harder to manage. So meshes are by far the most common form. We know how to use them properly. We can manipulate them. We can present them very, very quickly. We can take a composition with millions of triangles and render it with photorealistic quality within less than 10 milliseconds. This is actually what a high quality mesh looks like. This system has easily hundreds of thousands to millions of triangles. This image is generated in less than 16 milliseconds in hardware that costs less than $500. This is actually from Assassin's Creed. Some of you may be playing at the moment. This is what voxels look like. I'm kind of exaggerating a little bit to make the point. This is really not voxels. It's actually a mesh that is designed to look like voxels. Characters, actually move in a continuous way, but nevertheless, the tooling, the quality of the results are very different in the case of voxels. So this is where I'm going with this. As it turns out, researchers have started to apply machine learning to 3D shapes. So trying to do things like identifying what a 3D shape corresponds to, or trying to generate new 3D shapes from scratch. In many cases, this is done using voxels or equivalent representations, and the results so far haven't been great. So this leads us to question what the best representation is for the kinds of tasks that deep learning tries to do. So in particular, we are nowhere near being able to understand a 3D shape in the same way that we can understand a 2D image. The state of the art in 3D shape generation is even worse. For some 2D image tasks, we can do things basically with human level accuracy. And with 3D tasks, we're still in, is this a chair, is this a table territory? So let me, double down on that, right? In 2D, face recognition systems have become so good that we can distinguish a photo of one person versus a million other potential people, right? We can identify vehicles, pedestrians, the road, we can build autonomous car systems. In 3D, we don't know how to distinguish a table from a chair, much less understand, what the seat of the chair is versus the legs, right? I personally suspect that part of this is because we don't yet have a good way to compagine the previous knowledge of deep learning with our knowledge of 3D geometry. And we don't have the right representations that enable us to do reasoning with common 3D shapes. An interesting observation is that some recent research results use alternative representations to get better results. So here you can see different ways to approximate a 3D model. So on the right side, the authors used signed distance field, which is essentially a neural network that approximates that signed distance field. A signed distance field is basically a function that gives the distance between the camera and the object with some convention for the sign of that value. So this neural network predicts whether a point belongs to the object or not. In a way, the neural network encodes a representation of a 3D object in its weight. So I wonder if some breakthrough may come from looking at 3D shapes through a different lens, maybe finding a representation that enables us to play with these shapes in an easier or more powerful way. Let me repeat that to make it clear. Whereas before we were representing a 3D shape with points and edges and surfaces or discrete voxels or equations, here we are representing a 3D shape by the weight in a neural network that predicts whether a point in space belongs to the object or not. It's a very different way of thinking about that 3D shape. I'll go a little bit further. I would argue that this, what I'm showing you here, is a representation of a 3D shape. And maybe some of you recognize what this is. It's hard to get a reading of the room while doing a talk virtually, so I'll give you the answer right away. This is part of the DNA sequence of the gene that encodes a human protein. This is actually the part of the B chain of human hemoglobin, actually. So you may have seen it more commonly represented as this. Now, when I'm taking a little bit of a leap because in real life, it's not quite as simple as that, as this, but like the map that goes from the text representation I gave and the actual 3D shape is not really a well-defined mapping. There are biological phenomena like splicing and transcription to RNA, change in encoding, translation to polypeptides, and other non-deterministic transformations. Sometimes there are errors and so on. And sometimes different chains are not fully connected, and sugar groups may be added to the proteins, or heme groups, as you see here in green. They're not really as black and white as I'm showing, but the main idea, I think, is still valid. I think it's fair to think about a DNA sequence as an encoding of a 3D shape. Just to make sure that I'm driving this home. It's hard to overemphasize how important it would be to have a deep understanding of these types of shapes. Here I'm paraphrasing Galileo. He didn't really say this. The quote that is commonly attributed to him is, mathematics is the language in which God has written the universe. I think geometry plays a crucial role for so many tasks in biology that it may be justified to think about it as, geometry is the language in which biology is written. I think mathematicians in general haven't really spent as much time thinking about problems in the life sciences as they have about other problems in physics, for example. And we don't have time to go into a lot of the details, but I think in some ways, what determines how a living organism behaves and it operates, and a really large percentage of pharmacology and modern medicine is essentially determined by the shapes the proteins have, and how these shapes interact with each other in a predominantly geometric way. I think a really interesting problem is to find out what kind of 3D representation is more likely to help us deepen our understanding of the 3D shapes that that appear in this type of problems, and in particular how we can leverage deep learning to to solve this kind of problems in the life sciences. It's also hard to overemphasize the enormous economic impact that these problems have in society. Here is an image that some of you are probably already tired of seeing. This is a spike protein in the novel coronavirus, COVID-19, this virus thing that seems to be going around. Again, we don't have time to go into the details, but the way that our immune system responds to this is through antibodies, molecules that have a shape that is complementary to some part of this, so that it binds to it and neutralizes it, prevents it from doing its effect. I'm summarizing an immunology course in one sentence, right? So, take it with a grain of salt. But if there was a way that I could give you this shape, and you give me back another shape that is complementary to it, and most importantly, that is not complementary, by some definition of it, to the other tens of thousands of proteins that we already have in our body, and you could prove that it's not, and you could have made a lot of money. Maybe not a trillion, but certainly tens or hundreds of billions of dollars, right? This is, I think, in sharp contrast with the level of understanding that we have about these shapes. For some proteins, we have, names, for example, for some of the common structures like the helices and so on and so forth. If we look at, other, really complex mathematical problems, finite simple groups, there's a full classification of those, something that, was done over half a century and tens of thousands of pages. Or I think it's quite surprising that there is nowhere near the same level of effort, being dedicated to 3D shapes, given the importance that they have. Some of these problems could have enormous effects on our lives. Here's another example that I like very much from a company I follow. This is a simulation of cyclodextrin binding to 7-ketocholesterol. But their thesis is that the major component of cardiovascular disease, what causes atherosclerosis in our area, is the accumulation of 7-ketocholesterol, which is an oxidized version of cholesterol. So this happens to be very hard to simulate by macrophages. This is what causes the accumulation of the detritus in the arteria and eventually an infarction, a stroke or a heart attack. So what they're trying to design is a molecule that binds to it so that it's easier for our immune system to get rid of it. And they're looking at cyclodextrins because they're generally very safe. So if they were able to do that, they could potentially help prevent cardiovascular disease. This is something that kills 80 million people worldwide every year. So that's 10 COVIDs every single year. Let me reiterate that. If we could find a shape that fits this other shape, we may have a chance at saving 80 million lives a year. I don't know about you, but that sounds like a very impactful problem to me. I think it's very timely that there have been a few recent awards, being given lately to folks researching these types of problems, mostly from the computational side, but not really discovering a deeper understanding that truly solves the problem. On the left side, you can see the Breakthrough Prize was given recently to David Baker at UW for his contribution to protein folding. This is a $3 million prize, 3 Nobel Prizes in terms of money. And on the right side, there's another award given recently by the ACM to a team that was helping modeling the spike protein of COVID-19. And a nice coincidence, a couple of days ago, DeepMind from Google announced that they have created a machine learning model that predicts protein folding with about 90% accuracy, which I think is a very significant achievement. I think it's important to punctualize that this solves only one particular piece of the puzzle, right? So as far as I understand, this hasn't been used for purely novel proteins or to create shapes from scratch. And it also operates mostly as a black box in the sense that it doesn't give us deep theoretical explanations for why things are the way they are. But it's nevertheless something that was considered impossible with current technology until last week, basically. Maybe they heard I was giving this talk and decided to support me by announcing the solution of a 50-year-old grand challenge the day before. And last but not least, let's talk about analysis-like problems. if I may go back to AI, one of the interesting features of neural networks, which are the most commonly used models or algorithms type in deep learning, is that they are universal approximators. So what this means is that we can use neural networks to approximate any function within a set of constraints. This is something that they have in common. This is something that they have in common with other types of functions like polynomials, Fourier series, which are very well studied. So neural networks as approximators are maybe less studied because they tend to be very large and complex. And for interesting use cases, can only be calculated with a computer and not really by hand. I think it's interesting that we have been able to build approximations to some very, very complex functions. For example, an approximation of the following function. Given a conversation history, what is the next response? Okay, sounds good. This is a really complex function. I think 10 years ago, it wouldn't even make sense to ask, can we build an approximation to it? I think our understanding of machine learning back then and the technology would not have enabled us to provide an answer to it. Now, we all carry this approximation in our phones, right? And I want to emphasize the main idea here is that we know how to build approximations to really, really complex functions. So the idea that comes up is to what other functions can be built approximations, and especially approximations that are useful. So in physics, people have already started to do this, right? Starting with fields where the utmost accuracy is not necessarily critical. I actually learned about this from my work with companies in Hollywood, in the visual effects industry. Visual effects, the problem they're trying to solve is recreating complex physical phenomena like streams of water and how it interacts and flows around other objects, combustion, explosions, deformations of solid objects, kinds of things that you see in movies. But here they don't really care so much about whether the results are completely precise. They care about making it look real. So as long as it's similar to the real phenomena, it probably would look good on screen. So the main benefit, of course, is that it's much faster and easier. And in some cases may enable to obtain approximations that traditional methods would not have been able to do with current technology. So the next question that we could ask is, can we do the same thing? Can we use the same approach in mathematics? I imagine that we could build a demonstrably precise approximation to some complex object. Could we use that later, for example, to give bounds for how that object behaves under certain conditions? Or from another perspective, if we have a really complex mathematical object, could we build an approximation of it, learn from that approximation, and then extract information about the real object? In this case, the approximation may be much bigger in the sense that it requires more data, millions or billions of parameters, but it's intrinsically simpler because it's composed of much simpler objects, linear functions, sigmoidal functions. So the image that you see here is a representation of fluid dynamics, which is, phenomena explained by the Navier-Stokes equation, we believe. So I imagine folks have already started to think about, what can be, what can be applied to a problem such as this, right? But there may be hundreds or thousands of other problems to which we could apply the same reasoning, and we probably haven't yet. So let me clarify, an approximation is just an approximation, right? Even if we had an incredibly precise model, it would still not be the real object, right? But the question is, can we use this model, which is in many ways simpler, to extract insights about the real object, especially when we can operate or manipulate the simpler object, thousands of times faster than we can, with the real one. Let's go in a completely different direction. If you have ever played a game in which you could customize your character, you intuitively understand this. The sliders on the left side let you change how the character looks, but you can, and then you see the result on the right side, right? But you can think about it from a different point of view. If you take an image, there is an enormous amount of potential combinations of pixels. This is a space in millions of dimensions, right? So in that space, you have a very small subset that represent human faces from a variety of perspectives. So you could take that subset and try to design a map between that space and some vector space of a much smaller dimension, dozens or hundreds of dimensions. So this is essentially what the sliders represent, right? Values, in that vector space. So this map could have interesting characteristics, right? Like if you make small modifications to the sliders, you get small modifications to the pixels, right? So maybe you could think about it as, in some ways, the manifold of human faces, right? Hope that you can see my air quotes. I'm obviously being very hand wavy, right? I think it's interesting to consider what problems have these types of manifolds, right? And for which we can manipulate them. A little bit more formally, right? A few slides back, I talked about embedding spaces in deep learning. Essentially we had a space of words and we designed a map that goes to a vector space. We can take this idea further. We can consider the space of images, including all the pixels. And within this space, we take all those that represent human faces. And there are ways to do that, autoencoders or generative adversarial networks, commonly known as GANs. The actual method doesn't matter now, but this subset, it's not really well defined. Whether something is a face or not is typically described probabilistically rather than as a yes or no. But within our models, I think it's possible to consider this as some kind of space where we have a map that goes from pixels to a vector space in a small number of dimensions, and then from a vector in this space back into pixels. So this subspace is typically described as a latent space or a manifold, right? In the image above, what we have is a few points of the manifold of human faces and linear interpolation between them. So an interesting property is that small changes in latent space typically lead to small changes in pixel space. But again, this is not very well defined. The question that comes up, as you can imagine, is, well, this space is not necessarily a manifold in the mathematical sense, but how far is it from it, right? Can it be formalized? More importantly, can we do smart things with it and prove theorems in the same way that we can in real mathematical manifolds, right? Are there properties of certain problems that make it easier to find or manipulate these manifolds? And I think there are more questions than answers, right? Very few people have worked on this type of problems systematically. Now, the previous manifold may have been a little bit facetious, right? But here's an example with potentially much higher impact, right? In a similar way that we build a latent space for human faces, we can build a latent space for complex engineering systems, right? And here we want to ask questions like, is it possible to find a component or a system that has similar properties but is lighter, or has better structural integrity, or uses less material and is cheaper to build? For example, here we had a turbine. Can we make operations in latent space that lead to fans that are more effective, passing liquids, so that this engine, for example, is more powerful for the same cost? Obviously, this would have an enormous list of potential applications within engineering. And so far, I think we have very little understanding about what types of problems admit this type of approach. And even for those that do, how far this notion of manifold spaces can take us in order to come up with new real world designs. Here's a representation of what this kind of engineering approach could look like. This is Tony Stark, fictional Iron Man, designing a new suit. It's actually an area that I feel very passionate about. I actually worked a couple of years ago with a company that builds tools to create engineering systems. And it was interesting to speculate how far we are from something like this, right? The holographic displays is probably realizable in some form, but not as relevant here. Voice interface, it's mostly here. Like the missing piece to build this type of system is the ability to translate commands into smart engineering design decisions, not something trivial, right? Relatively trivial, like making a piece smaller or larger, but something deeper, like, can you make this part lighter while preserving the structural integrity of it, right? And we have tools that can do things like that for some subset of problems, but nowhere near the level that would make, something like, what is depicted in the movie visible. And I hope I have given you more questions than answers. Thank you for your attention. That's all that I had prepared for you today. I think we have a few minutes left. So I can take questions, and I'd be happy to connect on social media, answer any other questions that you have offline. Thanks again.
Thanks very much, Javier, for a very interesting talk. So I'll applaud on behalf of everyone attending. There are a few questions in the Q&A. If anyone else has questions, please put them in the Q&A function at the bottom of your screen. So the first question, Javier, is can you briefly explain why Moore's law is ending or dead?
Yes. So, there's maybe two answers to that question. Like one of them is from a purely observational perspective, right? Microprocessors have stopped getting faster and faster, right? There are, you can see over the past 2 or 3 years, the speed or the maximum performance that we get from general microprocessors has stopped increasing in the same way that it was for the previous 30 years, right? Now on an actual, basis, looking at the actual reasons, right? I think part of it is, we have reached physical limits, right? The speed of light, it is what it is. We can change that. Our fabrication techniques, it can only go that deep, right? Like you can only make transistors that are so many, atoms wide, and sometimes you can't go any smaller, right? Part of it, is the constraints in the fact that in a microprocessor, in a standard microprocessor, everything has to be within a 2D surface, right? So you have limits as to, the distances between the different components of the processor. Part of it is because general microprocessors have to perform a wide variety of functions and have to be compatible with code that was written 30 years ago, with instruction sets that were written many, many years ago, right? So that forces constraints on the designers of those processors. There are ways that people have been trying to move around that, and I think creating custom hardware for specific purposes is one of them, right? But I think in general, it's safe to assume that the end of Moore's law, as it was defined before, meaning that, no matter what we do in the software on the algorithm side, hardware will continue getting, twice as powerful every 18 months. That is not going to happen anymore.
All right, thanks for that. So the next question, I guess it's regard to hiring. With regard to these open problems, possibly amenable to mathematical insight, can you say something about the hiring environment and hiring on research end of industry?
I think it's a fairly generic question, and I'm not sure I understand exactly. I mean, if you look at companies that are trying to solve these problems, I would imagine any of them would be, hiring. I mean, I know for a fact that Google would be hiring, as many qualified people as we can find. People that would be, capable of working on some of these problems, right? I don't know how that works in the academic circles, right? But my understanding, right, is at Google, for example, right, like if you take a problem like the end of Moore's law, right, like the folks that can help design new chips, right, they won't have trouble finding jobs for sure. Within the biomedical sciences, right, I think we've seen a little bit of a surge this year because of COVID, right? There's an enormous amount of money and opportunities for people to work on really interesting problems, right? I think, maybe the only interesting tidbit, right, is that, mathematicians by themselves may not be 100% prepared to work on these problems, right? They may need to have some kind of interdisciplinary group, right, or collaborate with other folks in the industry. But I think any of the areas that I've been talking about, would have, an enormous amount of job opportunities.
Okay, thanks. So the next question is about other opportunities beyond research. What opportunities are there for mathematicians to make a material contribution at Google? So financial engineering, supply chain, marketing, analytics, etc. Which functions at Google have high concentrations of folks with advanced STEM degrees?
I would say, I mean, I don't know from the top of my head what percentage of Google is engineering. Google tends to hire higher than normal percentage of folks with PhDs for engineering jobs. Most of those jobs would be building software. We tend to hire not specialists with a specific area, but people who can build all sorts of different types of software, right, and can work across a variety of different teams, because internally it's very easy to switch teams, right? So we wouldn't have somebody that can work on only one specific area. But any of the teams that that are asking the question, right, would be good, right? Some of them have maybe more potential for growth than others, Yeah, I mean, it's kind of hard to give a numeric answer, right?
Yeah.
There's not so much financial engineering at Google, right? That's more on, quantitative finance and so on and so forth, but all the other ones would be, very applicable.
Okay. Another question is, are there other approaches to AI that don't rely on neural networks? So more specifically, are there any other promising approaches that you're aware of?
Yes, for sure. Yeah, I mean, so what I talked about is, in general, this dichotomy between discrete and classical approaches to AI and continuous or deep learning methods, or machine learning in general, right? So there's a distinction between the two approaches, but even within machine learning, there's a wide variety of algorithms that can be used, support vector machines and so on and so forth, right? Like there's a wide, boosted trees, right? There's a wide variety of different algorithms. I think the fact that we tend to speak in terms of neural networks is because there is an ecosystem, there are tools, there are hardware accelerators, there's an entire environment that makes using neural networks very, very easy, but they are far from the only game in town. Right? And if you look at some of the most successful approaches, ensemble models built of trees, for example, are really, really successful as well. Right? So it doesn't have to be neural networks. Neural networks are maybe a little bit more, elegant to study from a theoretical perspective, right? But they're not the only approach by far.
Okay. So I guess going in a similar vein of questions, with quantum computers and quantum algorithms, will there be non-trivial developments in this area?
It's hard to say. Yeah, I think there may be many changes that come with the advent of quantum computing. I feel there are some advances that happened over the past year or two, right? Is that there was a team, for example, at Google that was able to prove quantum supremacy on a problem that was a little bit peculiar, right? Not necessarily a problem that is interesting by itself. It was kind of designed in order to prove that. But there are problems that may admit interesting solutions from a quantum computer, right? I think a lot of those problems that we think of are in the context of encryption, for example, but they may be interesting also for AI. I think for AI, what people have been thinking about is more along the lines of, can we use quantum computers to make AI faster, but not necessarily get results that we couldn't get now, right? Whereas in encryption, the fact that something can be done significantly faster, that can be transformational, right? Because we rely on the fact that some computations are very slow to do in order to preserve privacy, right? In AI, not so much, right? In AI, one of the constraints that we have is how much data we have, right? So if we have an amount of data that can be processed by, a large supercomputer in a week, and a quantum computer can do it in an hour, that's great, right? That saves us money, right? But we can't just take that quantum computer and run it for a week because we just don't have enough data to feed to it for a week, right? So there are other constraints that happen in AI that I think will make it so that the advances are not as relevant as in other areas of quantum computing, I think.
Thanks. The next question again about jobs. Is there a website where we can apply for jobs regarding the research that you mentioned in your talk?
I don't think so, unfortunately. But if somebody is interested in something in particular, I'm happy to try to find a team at Google or DeepMind or any other alphabet company that may be doing something similar and forward the resume along.
Okay. Has DeepMind completely answered the problem of protein folding? Or is there valuable insight, e.g. cures against medicines, etc., in understanding the black box behind AI? And could you say a little more what role you see a mathematician be playing towards this goal?
Yes. So let me make a few observations. On the one hand, I think the achievement that DeepMind has made is very, very substantial. They have been able to do something that people thought it was impossible for many years. It was a problem that was posed over 50 years ago, and the best algorithmic approaches that we have were much worse than what they should, right? Like, the accuracy, the state-of-the-art accuracy within the same test that DeepMind solved was on the order of 30 to 40%, predicting the folding of a set of proteins, DeepMind was able to reach 90%. Now, does that completely solve the problem in a way? That depends on how we define the problem. I think the problem is not predicting protein folding. The real problem is if we have a specific health condition, how can we make a drug that solves that health condition, right? So that is a much wider problem, right? In which we need to understand, well, what is the molecular target that affects that disease, right? Like, how can we design a shape, or how can we design a drug that attacks that target? How can we make sure that that drug is not toxic or doesn't have other side effects, and so on and so forth, right? What is the manufacturing process, for that specific drug? There are a lot of other problems. So I think it's a big step in the right direction, but it's not necessarily a solution of the problem, right? Now, separate from that, I haven't had the chance to go through the DeepMind's results in detail yet, and I don't think they have published a research paper yet. But my understanding is that this model relies, same as most machine learning, on statistical regularities and a lot of data and a lot of compute power in order to do what it does. But it doesn't necessarily do it in an explainable way. It doesn't necessarily do it in a way that provides insight that may help us, deepen our understanding of this, right? So even if it's 90% precise predicting protein folding, it doesn't necessarily help us design a small molecule, right? Or it doesn't necessarily, help us come up with a new protein that binds to the one that has been predicted already.
All right, thanks, Javier. Following on, how big of an impact do you think computational biology would have in the world?
We are about to see. I think, this year has been incredibly interesting, right? Because of all the things that have been happening with COVID. I mentioned a few of the research awards that were given recently. I think all the stuff happened literally over the past, couple of months, right? So I'm hoping that, that it will have a really, really large impact. I think the variety and the impact of the problems in this space is tremendous, right? Not just in solving problems that we currently have, right? But even in making things better, right? If you think about how protein and protein structure, right, determines so much of how our bodies work, right? If you had a deep understanding of it in a way that you could, change things back and forth, right? Like, you could do things that we would consider impossible today, right? Like, can you, for example, fix tissue damage in cells, right? And could that help people live longer, for example, right? Can you create, going back to the example of hemoglobin, right? Hemoglobin is, not necessarily the most efficient way of packing oxygen in cells and distributing it, right? But it just happens to be the only, protein that we know that works in humans, right? But, there are other animals, there are other mammals, for example, seals, right? They can breathe once every half an hour, right? So if you could have and they use myoglobin instead of hemoglobin, right? But if you could design a hemoglobin that is, 10 times more efficient, right? And people could breathe only once every 5 minutes, right? Well, maybe that would have the effect that when somebody has a heart attack, for example, they wouldn't necessarily die right away, right? You can think very, very creatively about, different ways that you can improve, our bodies, right? To make them, more resilient, right? Or to solve all sorts of different conditions that happen right now, right? You can think about, different proteins that you could create that target cancerous cells for a specific person, right? And have really personalized therapies that cure a disease for a specific person, right? Like, that's something that we just can't do today. Even if we had the technology, right, it would be very hard to come up with something that is tailored to one specific disease in one specific person, right? And I think this is where, a lot of research money is being spent to this, right? So I'm fully confident that over the next 2 or 3 years, we're probably going to see, big advances in this space.
Few questions about collaborating with Google. What opportunities are there for academic research in partnership with Google? Are there any annual grant programs, for instance?
Yes, there's actually a variety of those. I have to say, I don't know from the top of my head. I know, for example, there are grants for PhD students. There are grants for undergrad and graduate students. There are internships for people to collaborate across summer. There are opportunities to collaborate as research associates. This is typically in areas in which Google has already established research teams. So it will be, databases, distributed systems, AI, and so on and so forth. So there are all those other opportunities. If there's something in particular, that this person is looking to explore, right? I think the best path would probably be try to find, if somebody at Google is already working on that. The Google research website, I think it's research.google.com, will have a broad list of topics and who's working on what, right? So, maybe reaching out to that person and seeing if there's an opportunity to collaborate, or, or being a visiting research or whatnot. I think Google is very flexible as far as, collaborating with external folks.
Yeah. So a similar question, if a research group in a university finds a solution for one of the problems you mentioned, how should they approach Google for a collaboration?
Probably open-ended. It would depend on which problem and which solution and how it could be used. I think that there are problems where Google, I think would be very interested. And let me punctualize that a lot of the problems that I've been talking about are not necessarily problems that Google itself is working on, right? But rather maybe Google with other companies, right? Those that are interesting for companies that I have worked with, as partners, right? So for example, creating engineering tools that help design more resilient, mechanical systems, for example. This is not something that Google does, right? But it's interesting for some of the companies that I've worked with, right? In some of these areas, people typically, publish research papers, and the collaboration is on an academic level. Sometimes, people, create software that solves some of these problems, and, there's a variety of ways, for partnering or licensing. To be honest, like the way that a lot of these things, typically work is somebody solves an important problem and they create a company, and then they commercialize it and they get some traction, make some money, and then, somebody else buys them, right? And integrates them into their product.
Okay. One more question. A PhD mathematician would bring strong research and math skills. What other kind of skills would one need to be successful in a tech environment like Google?
Yeah, well, I mean, the vast majority of people, even people that have PhDs that come from a research environment, write code, right? So Google hires, for the most part, people who write their own code, right? So I think that would be the most important skill. We do have research teams which mostly do research and write papers. They don't necessarily write code, but my first advice for somebody that comes from a purely theoretical background would be to know how to write software and to be able to write their own software. There are other companies that have research organizations in which there's a little bit more of a split, right? People that do only theoretical work and people that write, the software that supports that work. At Google, that's a little bit more rare. Like we typically like people who can do a little bit of everything, for the good or for the bad.
Is there any particular software language that you prefer?
It's hard to say. Python is great.
Python, yeah.
For a lot of these things, yeah.
Yeah. Okay, I think we went through our list of questions. If there are no further ones, I'd like to thank you, Javier, for a very interesting talk today. And I hope it has inspired a lot of the attendees to think more broadly about mathematics and where it can be applied. Thanks everyone for submitting your questions and for attending. And Matrix will not be presenting a seminar in January. It's summer holidays in Australia. But we will be back in February with a new online seminar. Thanks, everyone, and goodbye. Bye.
Thank you so much.